Okay, well, this is our last class of the semester. I know, openly weeping, single tear. It's been fun though, and I tried to pick out something that would be interesting and useful and fun for this last class, and so I thought we'd talk about the FFT in the context of creative digital audio. So just out of curiosity, rating your own familiarity with the FFT on a scale of 1 to 10, where 1 is, this is my first time hearing of the acronym FFT, and 10 is full mastery. Where would you all put yourselves numerically? 4, 5, 9, okay. 8, okay. Yeah. Yeah, somewhere in the middle. Okay. Right, well, okay, good. So then I won't spend too much time talking about what it is specifically, but the FFT is a version of a mathematical operation called the Fourier transform, which when applied to a continuous or a continuous signal or a sampled continuous signal, produces data that represents the sinusoidal decomposition of that waveform. And so the short of it is that it gives us access to harmonic by harmonic spectral information in a signal, and then gives us the ability to do stuff to that spectral information. So, you know, while we're used to sort of applying filters and maybe splitting up a multi-channel into individual channels, the FFT lets us sort of go even further and dissect a complex sound into its individual partials. And so it opens up a kind of a new realm of processing. So what I thought we'd talk about today is I first like to kind of give a walkthrough of, like kind of a visual walkthrough of the FFT, just so we kind of have a little bit of a better understanding of what exactly it is that's going on when we apply the Fourier transform to a signal. So that'll be just kind of pure language side, not making any sound, but using the language side FFT tools to pick apart a signal and put it back together. And then we'll get onto the server and show you the basic signal flow for doing FFT-based processing. Okay, and I've written down a lot of this in advance because it's a lot of typing, it's a lot of stuff that I'm likely to get wrong. So I've just dug up some old files from my computer. So if we have some arbitrarily long signal, something which is, you know, has a start, has an end, and which may or may not have periodic elements to it, like this water bowl, and this should come through in the recording. It's got this metal bowl with water in it and striking it while tilting it around, so it kind of makes this funny sound. We theoretically could use a version of the Fourier transform to analyze this entire sample and express it as a sum of sinusoids, with the fundamental having a period equal to the duration of this sound file. So it would be, you know, some sine wave that, you know, has some phase and some amplitude, and then, you know, we'd also get information for the second harmonic, which occupies 2 cycles of the space, and then 3 and 4, all the way up to the, you know, essentially the smallest possible frequency, which is just going to be, you know, a frequency that has a period of 2 cycles long. This would be a tremendous amount of data, and it would take a noticeable amount of time to do this. So it's costly, and it doesn't really help us very much if we're trying to do something in real time, because, you know, we don't have a time machine. We can't know what's going to happen. And if we want to do a Fourier analysis of something that's happening in real time, we basically have to wait till it's finished, and then we have all the data and we can do this analysis. So this is what we might call the discrete Fourier transform. So we're applied to a digital signal, a signal which has been discretized. So it is kind of interesting as something to, you know, mull over, that we can take a recording of an entire Beethoven symphony or something like that, and express it as a sum of sinusoids, which when summed will produce a periodic wave, 1 cycle of which is the entirety of that Beethoven symphony. It just means that the fundamental has a frequency of like 0.000000003 hertz or something, and it has like hundreds of thousands of harmonics. But anyway, so there's a variation on the Fourier transform, another version of the discrete Fourier transform, which is called the fast Fourier transform, which has some limitations, most notably that the analyzed chunk of audio has to be a power of 2. But the way it works is it's efficient to the point where it can be run in real time on a live signal. And so as we're talking into a microphone, we can be doing a spectral analysis using the Fourier transform, doing math with that data and putting it back together with a very, very minimal delay. So we're talking sort of like something like 512 or 1024 samples, which is a noticeable amount of time, but still pretty small. So, but so the way that works is if we were to feed this signal into the FFT, we'd first grab some power of 2 number of samples, and in that moment, this is the only thing that the algorithm would see. And so, here it is. But the FFT imagines, just for a moment, that this is the signal that we're actually working with, a truly periodic signal, one cycle of which is this exact shape. And so then it performs the FFT magic on this chunk of audio, and so kind of dissecting it and representing it as the fundamental of this time period and second, third, fourth harmonic, etc. And then we have that data. We can do math with it, and then resynthesize it back to this what we call the time domain, and then we move on to we slide over by some amount of the initial time domain window, and then we do the same thing again. This becomes our cycle of our periodic waveform. So it's a lot of stuff, but it all happens very, very fast. And so what I've done to kind of demonstrate this a little bit more clearly is I have pre-rendered this sample from somewhere in the middle of I think it's a piano sample. So I've just gone in and done a little bit of private sort of audio engineering just to make this so that it is exactly 512 samples, and I've edited it a little bit, but this is what it looks like, and it sounds like this, very, very short. That's what 512 samples sounds like. Okay, and so we're imagining that we're somewhere in the middle of this ongoing FFT process, and I've loaded the that buffer data into a signal object. So it looks exactly the same. Here it is, just stretched out across the whole screen. And we're going to perform an FFT on this time domain signal. And this is the language side math, which does this. It's an operation which involves complex numbers, and so we prepare an empty signal for the imaginary part of these complex numbers. We already have the real part, which is the signal itself. We prepare some other stuff, and this is the actual take the FFT of the real and imaginary parts, and here's use this cosine table to do the operation, and then we can call magnitude and phase on the complex number array result to extract what is essentially the amplitude and phase offset of each harmonic in this I think it's 512 samples. Yeah, 512. Okay, so let's do it. And this is the result. It looks kind of wacky, so let's. I'm gonna press M a few times to display this as a histogram. It's still a lot of data. So we have this sample size of 512 samples, and so the highest frequency that can be represented is one whose period is 2 samples long. And so that's basically if it's the 256th harmonic of that space, and everything beyond that is going to be a mirror image because of aliasing. That's how I've always understood it. So you can see that the magnitudes or the amplitudes array on the top here is a mirror image of itself, and so everything above the halfway point is really not necessary because we already have that data, and it just represents alias frequencies, which we don't really care about, and we don't want those there. And then this down here is the phase information, and it's a range from, I think, negative pi to positive pi, and it's the phase offset of cosine functions. And this is a lot to look at, and so what I'm going to do is draw it more selectively and only look at the magnitudes and phases of the first 30, what are called bins. In fact, I'm skipping the 0th bin, which represents the DC offset, basically a cosine function which has a frequency of 0. It's just a horizontal line, and we don't really need that. So now what we're looking at is the amplitudes of the first, second, third, etc., up to 28th or so harmonics, and these are the phases. And so the phases, if it's flat, it's just like a perfect cosine wave, starts at 1 and goes down. So I think that the thing to focus on is the amplitudes here. And what I'd like to do now is reconstruct it piece by piece. So I'm just going to start by taking only the fundamental. And so what we've got here is the sine waves, the individual sine waves reconstructed from the bins that we're using over here, the sum of those harmonics, and the original time domain signal, which will eventually take shape from this sum of sine waves. I'm sort of torn on whether I should scale the plots. Here's what it looks like when I just let them normalize themselves. The amplitude is not going to be represented accurately, but we can see it a little bit more clearly. Actually, I think I will just keep them on a static scale here. Okay, so let's take the first and the second. Okay, so here we have the fundamental, the second. We add them together, and we get this kind of shape. And already you can kind of see it's developing a profile similar to the original segment here. So let's take 4 of them, and we're starting to get more and more resolution. Here's 6, 8, and 10, and I sort of run out of space here, so they start stacking on top of each other. But 12, and also it's something to, well, let me do this again, and we don't really care about you. So we can see that the amplitude of the first harmonic is sort of somewhere in the middle. We have a lot of energy in the second harmonic, consistent here, less in the third, and then not a whole lot in 4, but 5 and 6 and 7 get progressively higher. And then a little bit of, once we get to 15 or 16, there's a very small amount. There's just not a lot of activity at those. So if we go up to 16, here we have the original waveform, and here we have a sum of sine waves. And even without all of the bins factored back into the resynthesis process, we get a pretty nearly identical version. Right? And this works no matter what is in this original, even if it's like a sine wave whose frequency is continuously increasing or decreasing. You might think there's no way, we can't use a discrete fixed frequency harmonics to reproduce this, but you actually can. It just involves a very precise recipe and energy at all frequencies with very specific phase offsets, and it can be done. Yes, question?
So is the fundamental going to always be a frequency equal to the sample rate divided by the window size?
Yes, the fundamental, quotes, scare quotes, fundamental of the FFT process is based on the sample rate and the size of the power of 2 size of the window. And you can say, well, okay, there's going to be a lot of sounds, the actual content of the waveform, which has a frequency which does not fall into one of those frequency bins. If we have some frequency content which occupies a non-integer number of, which undergoes a non-integer number of cycles in the span of that FFT window, we're not going to be able to cleanly represent that with energy in one bin and nothing anywhere else. We have to use, we have what we call spillage into adjacent bins. It's kind of an interesting thing to watch, and that's actually a pretty good pivot to go on to this animation that I've created. So we'll do it quickly, and then I'll slow it down. So here's what it looks like. And you're seeing some power of 2 time domain window on the top, and then the magnitudes and phases for the resulting FFT on the bottom. So I'll slow this down a little bit. Oops, now it's going crazy. Let's try that again. There we go. And just initially, right when it's sort of just a flat line, we have energy here, and then right now we have pure sort of energy in the first harmonic and nothing anywhere else, and now we have perfectly aligned with the second and the third, etc. But whenever we have a non-integer number of cycles here, the decomposition, Fourier decomposition, necessarily involves actually all of the harmonics. Most of the energy clustered around what the frequency of this is. If we have like 4.5 cycles, we're going to have energy in bins 4 and 5. But then everything else also has to sort of chip in and give a little bit of its energy at its frequency with a very specific phase offset, so that when reconstructed with all bins, we get this exact shape up here. So I just think it's kind of interesting to see. I mean, this is all pretty predictable. We see just when we have perfect alignment, we get energy in one bin and nothing anywhere else. And then here's how the phase offset information has to be calculated. I have a couple other examples. Like here's a sawtooth wave that transitions to a triangle wave and back to a sawtooth wave. Oh yeah, I have to close all these windows first. That's quite fast, but we can maybe slow it down. So the sawtooth wave is energy at all bins with a sort of exponentially decreasing amplitude right there. And the triangle wave is only odd harmonics. So just for a moment in the middle, we get only 1, 3, 5, 7, etc. Yeah, so this is all delightful and well and good. Yes?
Well, and sorry for just the clarifying.
No, go ahead.
So then as we increase the window size, the fundamental gets lower, and because as we increase in harmonics, the frequencies become closer together. That's why it said that a longer window size is more accurate, correct?
Yeah, I wouldn't phrase it exactly that way, but you are correct. If here, we're in this example here, we're picking, I've engineered a situation where we have an FFT window size of 512 samples. Mm-hmm. So, whatever so the fundamental is the sample rate. I think that's my sample rate divided by 512 is 93.75 hertz. So that's the lowest frequency being, analyzed, and then multiples of this. But if we were to do 8192 window, then we have a fundamental of 5.8 hertz. And so the harmonics are again spaced at intervals of this number. And so we get a much finer, more bins, right? There's going to be a sort of longer time delay in the analysis process because more samples have to occur before we can start analyzing them. But we get a very, very fine resolution of frequency information. Yeah, and so the general trade-off is that a big window, and when I say big, generally I have seen 16,384, but once you get higher than that, you're dealing with a delay of like a quarter of a second, a half of a second, and then it's not as useful in real time anymore. So 8,192 is like sort of as big as you can kind of deal with without sacrificing in a significant way. That's really good for retaining high precision spectral information. What you lose is time coherence. So any sort of short articulations, things which are crisp and clear, like percussion sounds and things like that, those will, on resynthesis, those things will get kind of smeared just because of the size of the window. But if you go down to like 512 or 256, then you're dealing with a very, very fine resolution of the time domain and like doing analyses of really small chunks of time. but you have a very coarse frequency resolution, and so spectrally rich sounds are going to be sort of misrepresented on resynthesis, but you will still get a pretty good representation of your articulation profile. So that's kind of so it's really context dependent. There is no perfect FFT size. It's just you use what is appropriate based on what it is you're trying to do. Okay. So I've got the server booted, and let's do some very basic FFT synthesis and resynthesis. And we can make synth depths. I suppose maybe we will. We'll see. And I'm going to grab some sound files that I've prepared in advance. I'll change these paths so that they'll be relative paths, so that it'll be more easy for you to play with this. But this is a metal yardstick with the markings are actually engraved, and so scraping a piece of metal against this yardstick kind of makes a cool sound. Yeah, so that's fun. And let's just make a very simple UGen function. I believe this is a one-channel file. Yeah. Right, there we go. We've got our looping playback. So it's basically a three-step process here. I guess two at minimum, where we have to apply the FFT operation to this time domain signal, and then we have to resynthesize from Fourier information back to the time domain. So what most help files will do is declare a second variable called chain. Of course, you can call this whatever you want. And we'll say chain equals FFT. And this is not a UGen, so we don't say .ar or anything like that. It's an object. And I think that the method is probably .new. Yeah, FFT.new. So we can put that there if we like, or we can omit it. And we need to provide, at minimum, two things. A buffer, which is the correct size, which has to be a power of 2, basically. And so and I think we probably could do this by saying, b equals buffer.alloc and making it something. I've never really tried that. What all the help files do is use a convenience class called local buff, which will just do the allocation for you when the synthesis process runs. And we provide some power of 2. If I had to, my deserted island FFT size would be 2048. I feel like if I'm stuck with one for the rest of my life, I think it would be 2048. And it's a one-channel file. This is monophonic, so we just need a single buffer. And then we provide the time domain signal to be analyzed. And what is returned and held in the chain variable is basically a buffer which contains the FFT information of the current piece of 2048 samples that was analyzed. A couple of help files just to point out here. FFT overview is a good read. And I think this is where it tells you what is actually stored in the buffer, where we get information about DC bias, the Nyquist frequency, perhaps. But then here we have pairs of basically complex numbers represented as real and imaginary parts. Not actually magnitudes and phases. We'd have to sort of extract that ourselves if we want. But the whole point of the design here is that we don't really have to think about it too much. Okay, so if we didn't want to do anything, we can just say sig equals IFFT, inverse FFT, and we say give me the name of the buffer containing FFT data. That's chain, and usually this is fine. If this were a synthdef, we'd then need to use out to write it. But since we're just using function.play, we can just do this. And so what we've done here is in very fast motion, this exact same thing that we were doing earlier, where we kind of dissect this sample and then piece it back together with sine waves. So we're kind of just taking it apart and putting it back together. And so it sounds exactly the same as we would expect. But inside the FFT, IFFT combo is where we can start applying these various, what SuperCollider calls phase vocoder UGens. So let's go into Browse and go to UGens and go to FFT. And I'll make this a little bit bigger. So there's a bunch of fun stuff here. There's the FFT object. And we go down to the PV area, and everything, all these PV underscore this, PV underscore that. These are UGens, in a sense, which operate on an FFT buffer rather than a time domain signal. Some of them, for me, have this plus classes. They are part of the SC3 plugins package, which is if you go to github.com/SuperCollider, you can then go to SC3 plugins, and I think most of the PV extensions are in a anyway. But you just go down here to latest, and pick your there's a whichever operating system you're using, and there is a README which sort of tells you where you need to put it. You basically unzip, you find your extensions directory, and you move the SC3 package into that extension. So I've done that already. So what you see here is going to be a larger collection than what you see if you don't have the plugins installed, but it's pretty easy to install them. So let's do we'll do bin scramble. So I think again this is a .new situation, but we don't really need the .new, and I don't think you'll see it in most of the help files. So we provide the FFT buffer, and these PV UGens just do the math and then replace the new data over the old data. So we don't it's not sort of keeping separate buffers of these things. It's just kind of overwriting it with each operation. So we're just going to overwrite the new FFT information here. And okay, what does bin scramble do? It randomizes the order of the bins. So we've got our bins, and it's just going to take the magnitude and phase information and then swap them randomly depending on the parameters. 0 means none of the bins get scrambled. 1 means every bin will end up in a different random spot. And something like 0.02 is going to randomize just a few of them. Width is how far a randomized bin will move from its original location. So I think 1 means it could go from lowest to highest, and something closer to 0 means it's not going to move very far. And so this is actually kind of an interesting parameter, because by keeping this low, we preserve a lot of the original character, I think, of the signal. And then we can use a trigger signal, an argument, or another UGen to say randomize again, randomize again, randomize again. So a lot of flexibility here. What I'll do is we'll wipe all the bins, but keep the width pretty small. So all of them will just kind of randomly move a little bit. And we'll just trigger this once and be done with it. So again, here's the original sound. And here it is with some scrambling. Let's see, even more scrambling. And then we can do something like 4 random rescramblings per second. Anyway, so you can hear this, it sort of becomes just kind of a swirling mass of Fourier sine wave stuff once we sufficiently randomize it. Okay, so and you can also follow this up with another PV UGen of some kind. Let's see, I'm trying to remember the ones that I wanted to cover here. what have I done here? Oh, rand, let's look at rand comb, just to give another example here. And let's get another sound file as well. I have this flute recording. And I know this is stereo, but I'm just reading one channel in. So that sounds like this. Yeah, short kind of timbral trill thing. So PV rand comb has a wipe and a trigger, and so it just zeros magnitude and phase for random bins depending on a value from 0 to 1. All right, so and then the trigger is going to randomly wipe, there's something called PV rand wipe, which is, I think, a little bit different. So we'll say, so I think 0 means don't wipe anything. Yeah. So 0.05 semicolon. Of course, every time we run this, it's an entirely new synth def and synth, so. And the higher you go, the higher the likelihood is that you're going to remove a lot of the bins that actually have good beefy content in it, because there's so many bins, which are just up there close to, the Nyquist frequency, which are just not going to have a lot of data in them. And so if only those are left, it's going to be really quiet. So, everything is influenced by context and what's actually in the sound that you're working with. So, now we're getting closer and closer to the stereotypical FFT sound here. Yeah, if there is one, I don't know. Yeah, there's like all things, easy, like dynamic range processing, compression, granular synthesis, FFT-based processing, easy to do, easy to overuse, hard to turn it into something really musically compelling. So there's just because we have access to spectral information does not mean suddenly our jobs as creative composers is easy. In fact, it's probably harder. So anyway. Let me do an example with a stereo sound source. This is important. So we are going to read. That is technically a stereo recording, but it's just a flute, so the channels aren't that different from each other. So let me get this forest and birds recording that I made. So that is, take this. And this is a 2-channel recording. And I know it's pretty quiet, so I'm going to amp it up a little bit. So if we just run this as is, there's 2 channels of audio, but only 1 buffer to store the FFT data. So this is not, probably what's going to happen is the second channel is going to get dropped, or we're going to get some error message. I'm going to, I can't hear from where I'm sitting. Is this just 1 channel? Yeah, okay. So it simply just ignores the second channel. So the wrong way to do it, as the is it this file that tells you? No, I think it's I'll find it. Where is it? Is it this one? Yeah, in the FFT file. It's one of the very first, colored, hello, alert, pay attention to this kind of things. To do FFT processing on a multi-channel signal, we have to provide an array of mono buffers. Although SuperCollider does know how to allocate and use multi-channel buffers, this won't work in this context. So, there is an argument, the second argument of local buff, which is the number of channels. And so we think, okay, yeah, I'll just do this. will not work. I'm not sure what's going to happen, but this is the wrong way to do it. Instead, we provide an array of mono buffers. So this is our good friend, duplication, or on a function, which gives us. Oh, and this isn't going to work because it's a, it's a UGen, or what is this? Yeah, it is. Local buff is actually a UGen. So I think this is just getting grouchy because it's like outside of the context that it needs. But if we just do, this, we get the contents of that function evaluated and created 2 unique times. And that's what we need for local buff. So chain is, we're using FFT, and we are passing it an array of 2 mono buffers, one for the left channel, one for the right channel. And this should work. Right. So now we have our gorgeous forest recording in true stereo. So I think everything else inside the doing all the FFT processing is the same here, because chain is a it's this array of 2 FFT buffers. So let me see if I can come up with another interesting example. I'll tell you what we'll do. Well, let's just do. Let's go back to our browse. UGens, FFT. Well, I know freeze is an extension, PV freeze. It's in the Josh Parmenter's package. But you give it a trigger. When freeze is positive, it will hold the magnitude data, and then I think it will try to advance the phase data to avoid a discontinuity or something like that. I don't know how the guts of PV freeze works, but and I'm just going to say trig.tr1. Have we done this in class? Have we done the TR before? Okay. We know, when we're making control arguments, KR gives us a control rate argument that we can set. AR is audio rate. IR is initialization rate, which is an argument that we can't set other than its initial value. TR is a trigger argument, and the way these work is that when you set them to a positive value, they will hold that value for 1 control cycle and then snap back to 0. So a KR version would work, but we'd have to manually set it back to 0. But this is expecting a trigger. Every time a trigger arrives, it will freeze. But if it's KR, we'll have to manually unfreeze it. We don't really want that. So actually, let's start this out at 0. Semicolon. What did I do wrong? PV freeze. You know what? Maybe it's not supposed to be a trigger. I think it actually, this is exactly the kind of case where we don't want to do this. There we go. Yeah. I thought it was going to freeze when it gets a trigger, but then I guess there'd be no way to unfreeze it. Okay. Yeah. This is a good example of, let's see what happens if we drastically reduce the size of the FFT buffer. Right. Now this is the sound of the sum of sine waves at this point in time. But remember, we're dealing with a fundamental of like 93 hertz or something. So, we've just kind of added these all together, and this is what we get. So if we're trying to do spectral freeze, we generally are going to want a higher FFT size. And this gives us a much better resolution. Yeah. Let's do something with one of the questions that always comes up, and it's a very good question, is how do you blend the spectra of 2 different sounds? And I don't think there's like a definitive recipe for this. I mean, the thing is, you just do an FFT of two signals, and at every single frame you have magnitudes and phases of one and magnitudes and phases of the other. And then how you want to combine those mathematically, well, there's like a million ways to do it, right? You can interleave the bins. You can take the magnitudes from one and the phases from the other. And this is where my conceptual understanding really kind of breaks down, because I do not really have the vocabulary to translate between math applied to magnitudes and phases and practical sonic results of those operations. So I just kind of experiment and try things. But there's one built-in called MagMul, which is it multiplies the magnitudes of two inputs. So basically, if there's energy in both bins, some positive value, you multiply them and you're going to get some positive value. But if one of them is very close to zero, the multiplication operation will result in something very close to zero. And so shared spectral information will be preserved, and information that's not shared will tend to be eliminated. So this is a candidate for some sort of spectral synthesis, or cross synthesis, as it's called. And it keeps the phases of the first input. So this is not a commutative operation. The order in which you present the two FFT buffers will matter. And let's try to do, let's see, I want that water sloshing file. So we'll grab that one. And we'll blend it with the flute, I guess. So we have flute. And we have our
lowercase o.
Yes, not zero. H2O. Thank you. So let's just see what happens. I don't know. It's hard for me to predict what it's going to sound like, and even if we keep the even if we do the same cross synthesis operation each time, I don't know. We'll see what comes out. We'll copy you. I guess we sort of need sig A and sig B. And so that's our flute. That's our water, sig A, sig B. And then we also need chain A, chain B, FFT, H, sig A. Okay, so now we've got two separate FFT buffers operating on two different signals. And so then we can say chain A equals PV mag mul. And then we'll say sig A and sig B. And so it's, again, these UGens, it's just going to write, it's just, chain A, what am I doing? Chain B, right? It's going to do this multiplication operation, and then I think it will just overwrite the first one, so it ends up getting stored in chain A. You can also, make a new, it's all fine, it just gets stored in whatever. And then I guess might as well do this. And let's see what we get. This water is two channels. That was kind of cool though. So let's do read channel, only that one. I'm just going to overwrite it. I know that's bad practice, but that might be clipping a little bit. Now let's see what happens if we reverse the order. I can't exactly tell you why it's different or sort of how it's different. I just know it's using the phase information from, I think, the first one. Yeah, so it's using whatever phase data was extracted on analysis of the water bowl sample. So there's a lot of details I'm kind of overlooking here. In the FFT UGen, there are some additional arguments. There's the hop size, the shape of the windowing function, and then some other things. So hop size refers to the amount by which the FFT window will advance through the time domain signal. And 0.5 means half of the window size. So we're doing an FFT on the first 2048 samples, and then we slide by 1024 samples, and then slide by that much every time. So we're kind of doing a 50% overlap. We can make this 0.25. I'm not sure what valid values here, but obviously if you do something bigger than 1, there's gonna be gaps, and something to experiment with. 0.5 and 0.25 are pretty typical values. And then window size, oops, that's not what I meant to do. What's going on here? Oh, my keyboard layout has changed somehow. All right, window type is either -1, 0, or 1. And we can't actually plug our own window in there. We're stuck with, the default is a sine window. It's basically an upside down cosine function. It says typically recommended for phase vocoder work. The Han window for analysis work, and then the rectangular window is basically the absence of a window. And so you will get clickier, crunchier things. So let's keep that the same. Let's use the Han window just to hear how it changes. And we'll use the Han window for analysis as well here. And I'm going to bring this back to our original. I think this one sounded better. Versus sine window. I think this one sounds a little better. So the windowing is basically we take our FFT sample of the signal, and then when we do this sort of analysis, it doesn't do it as is, but it will actually kind of apply this windowing function. I'm just kind of coarsely doing it here. So it actually fades in and fades out. And this is to, it distorts the spectral information, but it makes the result much smoother and cleaner. I think it avoids, I think it just avoids like discontinuities and clicks. And I think you can, if you just use a rectangular window, you'll hear what it sounds like if we don't window. There was one more thing I wanted to get to, and let me see if I can do it very fast. There is a DIY option. If you can't quite find one of these that does exactly what you want with the magnitudes and phases, you can call PV calc on an FFT buffer. And PV calc is it's a method which will essentially iterate over the bins. Not exactly, but that's conceptually what it's doing. So we say how many frames are we working with here, and we give it a function. And in that function we define 2 arguments, magnitudes and phases. And so this represents the array of magnitude data for the current frame, and this is the current phase data. And so then we just need to return an array of the same thing. So this should just be the normal yardstick. And there's actually a noticeable delay when we run this function, more than usual. And this is probably one of the most computational ways to use the FFT tools in SuperCollider, because it doesn't look like it, but it actually results in a very large synth-def. And I think that's where the delay comes from. The process of building the synth-def is complicated, because I think this is basically the equivalent of a synth-def with thousands of UGens in it, because for each bin call, it needs to, I think, plug in one of these pack and unpack FFT UGens. So it's not efficient. So use it judiciously and carefully. But we can do things to mag and phase here. For example, let's say mag.rotate -20. So what this does is I think it just basically shifts the data. We'll just do it with an array here. So if we have the array 1 through 20 dot rotate -5, we get this. Right? So it kind of shifts the information, takes the indexed items and shifts them to the left by 5 and puts the other ones, the ones that fall out, back on the other end. And so I don't know what this is going to sound like, but we have to say, we have to say mag equals rotating. Right? Let's do the flute here. That might be more interesting. And now you can't put a UGen here, I'm pretty sure. Like if we did like a sine-osc here or something, something is going to happen. Like I'm not totally sure. It doesn't like it. But there is a way to do dynamic things here. And I think what you have to do is you have to, I haven't tried this, so I'm not going to try it now. But I think you just define this out here. And then you can refer to LFO, maybe? I don't know. Yeah, I was browsing sort of the SuperCollider forums, and I was just kind of looking for examples of PV. I think I saw something along this line. So, I guess I would encourage you to experiment. But anyway, this is there's also PVCalc 2, which is a way which expects a second FFT buffer, and then you declare mag phase, mag B, phase B, and you have access to magnitudes and phases of 2 different FFT chains, and then you can cross-synthesize them however you want. And there's also PV collect, which gives you magnitudes, phases, bin number, and index. And I think these are the same number. I'm not actually sure. I think it's a little redundant, but just in case you want a sort of incremental counter in the context of this function, you can do that as well. And these are in the is this the PV chain UGen file. So the PVCalc 2, and so yeah, it's worth experimenting, I think, with these as well. Just delete this. Okay, well, I hope this gives you some interesting stuff to chew on, and I would definitely recommend the extensions, the plugins to augment your PV library. There's a lot of fun stuff in there. I have a mini tutorial which is time stretching using PV record buff and PV buff read. So that's basically time stretching without influencing pitch, and with a high FFT size, it's pretty good quality sound. And yeah, so I guess that's it for classes this semester. So keep in touch as you work on your final projects. I'm happy to take a look at things and give some guidance and feedback if necessary. And I think we've set a date, right? What was it, 1 to 4 on the 13th? 13th? Okay. Which I think is also when the optional homework is due, the GUI homework, for those of you interested in doing that. Okay. Well, good luck on your exams and the rest of the semester, and I'll see you on the 13th.